In a region of space 650 light years from us, there is a ticking time bomb. When it detonates, it will unleash a wave of fiery radiation and incendiary matter careening across the Milky Way galaxy, devastating objects in its path. Planets that are too close will be ripped to shreds, their stone turned to magma, their atmospheres stripped away. And this time bomb is near enough to us that if we raise our eyes at night, we can spot it unaided. It is one of the brightest objects in the night sky. It is Betelgeuse, our closest red supergiant, and it will soon go supernova. But how soon is soon? Centuries? Years? Days? And what will that mean for us on Earth? In search of answers, scientists have studied this volatile behemoth as it teeters on the brink of annihilation, seeking to unravel the processes and signs that foretell its imminent destruction. And as its timer ticks ever closer to zero, we keep finding ourselves being surprised. I'm Alex McColgan and you're watching Astrum. Join me today in this Supercut as we discuss everything there is to know about Betelgeuse, including incredible new discoveries that have been made in recent years, with one little secret hidden in its shadow. As always, let's start with some of the basics. Betelgeuse is the 10th brightest star in the sky, easily visible as the left shoulder of Orion. If you do look for it in the night sky, it is also visibly redder than any of the surrounding stars, and it does a lot of twinkling. Its color is expected for its category. Betelgeuse is a red supergiant, or a medium mass star. Red supergiants are far larger than our Sun, and Betelgeuse is no exception. It has a radius that extends beyond Mars's orbit. Betelgeuse is almost 900 times the radius of our Sun, but maybe only 10 times more massive, meaning its density is much lower. Its mass is spread out so much that Betelgeuse's gravity is tiny. It can barely keep itself from escaping into space, which is why you see these huge convection cells bubbling on its surface in this computer model simulation. Just imagine seeing a sunset from a star like this. But of course, the thing that you are probably most interested in about Betelgeuse is its impending demise. Supernovae in our galaxy are not that common. While astronomers observe hundreds of supernovae every year outside our galaxy, this is mostly a reflection on how many galaxies there are in the universe. Closer to home though, within our own Milky Way, we likely only see about 2 to 3 every century. This means that the odds of one going off tomorrow are not that high, but they're not impossible. So what might be the impact of such a detonation? Of course, it all comes down to proximity. Interestingly, according to archaeologists, the Earth has likely been hit by a supernova before in the course of its 4.5 billion years of existence. For starters, we exist in an area of space known as the local bubble, a relatively sparsely populated region of interstellar space about 1,000 light years across that is thought to have been carved out by a supernova detonation 10 to 20 million years ago, which our planet would have been around for. I talk about that in another of my videos, which you can see here. Scientists have found evidence of another detonation that happened 2.5 million years ago due to a high concentration of iron-60 and manganese-53 in a particular layer of the geological record. This supernova happened far enough away to be harmless to us, but this might not always be the case. There are some scientists who believe that the extinction of woolly mammoths was caused by a massive piece of debris from a supernova crashing into the planet about 13,000 years ago. The impact site in question had magnetic spherules and radioactive potassium-40, a substance found in supernova ejecta. A smoking gun in the era most mammoths went extinct. Even before that, mammoth tusks from 34,000 years ago were found containing tiny impact craters from grains of slightly radioactive iron that had been traveling at 10,000 kilometers per second. Perhaps not coincidentally, that is one of the potential speeds supernova explosions travel at, namely between 10,000 and 40,000 kilometers per second. That can't have been a nice experience for the mammoths in question. On that note, going back in time like this in the geological record can help us gain fascinating insights into our planet's history. But learning about your personal history can be even more profound feeling. Today's video is in paid partnership with MyHeritage, a leading family history and DNA testing service that helped me learn more about my own family, such as my grandfather. I don't have a large number of memories of my grandfather, as he lived in Ireland and died when I was relatively young. But I went on MyHeritage and I was able to discover he had 5 siblings I never knew about, many of whom died in infancy. It was a profound insight into the challenges this man lived through, even as the main memories I have of him were his kindly smile. I was amazed at how easily I could find more information about my ancestors. Once you fill in what you know about you, your parents and your grandparents, the magic 7 as MyHeritage calls them, MyHeritage draws from its 36 billion plus historical records to find possible matches. Connecting to other trees takes just a few clicks, helping you discover all these moments you never knew about. It's captivating, but also oddly grounding as you learn who you are and where you came from. MyHeritage's enhancement tools really bring your old photographs to life. So if you want to find out more about who you are, scan my QR code or click the link in the description below to give MyHeritage a try with a 14-day free trial. Now, back to the wider Earth's history. An astute observer from this might be able to note an important fact, however. Evidently, if life began on Earth about 3.7 billion years ago, and we faced 3 supernova explosions that have impacted us in the last 20 million years, and life is still largely ticking along, my condolences, woolly mammoths, if you did die out from one of these, then supernovae as a whole can't be quite as destructive as my opening introduction made them out to be. Well, not quite. As I said, it is a question of proximity. If I'm 1,000 kilometers away from a nuke going off, I have little to fear. But it's a different story if one detonates on my coffee table. And when it comes to supernovae, it turns out that the universe has relatively large coffee tables. To understand the scale of these explosions, it's necessary to understand the forces involved, which means we need to understand a little better about how supernovae, like the one brewing inside of Betelgeuse, happen. It turns out that there's 2 main paths stars can take to get to that explosive grand finale, although in each case it has to be the right kind of star. For the first path, resulting in a type 1a supernova, it usually needs to be a white dwarf in a binary system that's gradually or speedily siphoning matter away from its neighbouring star until it reaches a point of critical mass. This path is not fully understood, but it's thought that a white dwarf, or a dense star comprising of mostly carbon in a giant superdiamond core, is normally finely balanced between 2 powerful opposing forces: electron degeneracy pressure and gravity. This simply means that atoms usually object to being squashed too much. Their electrons like to remain at certain distances from the nucleus of the atom and will resist being pushed denser than this point. But gravity is an incredibly powerful force that seeks to draw matter closer, particularly in a dense mass like a white dwarf, where a section the size of a sugar cube has the mass of around a car. And in a binary system where the white dwarf is absorbing more and more matter from its neighbouring star, eventually gravity overwhelms electron degeneracy pressure and the whole house of cards collapses at once. Carbon fusion begins. Within a few seconds, most of the star undergoes fusion, forming into heavier elements and releasing a whole lot of energy as the matter in the star settles into its slightly more efficient new configuration. How much energy? around 1/4 joules. That's 1 followed by 45 zeros. If you claim you knew that number before, you're almost certainly a liar. All of this energy is released in just a few seconds. So naturally, the star ejects its entire contents out in all directions, sending it traveling at 6% the speed of light and unleashing a flood of mostly gamma radiation out across the galaxy. The brightness of this event is 5 billion times brighter than our Sun and burns for a few weeks until the ejector has traveled far enough that the overall energy level has started to dissipate. The second type of supernova, type 2, is similar, except instead of involving a white dwarf, it involves a massive star at least 5 times more massive than the Sun at the end of its lifetime. And this is the type much more relevant to Betelgeuse. These stars are still burning brightly, and rather than just electron degeneracy pressure, it's also the heat of fusion that keeps the star in balance, converting hydrogen to helium. This fusion creates an internal pressure, which combats the effects of gravity, wanting to compress the star into a smaller volume. However, eventually the hydrogen fuel in the core will run out, having been converted to helium, meaning the fusion process stops and the star's core can't overcome the effects of gravity anymore. The core compresses, but if the star is massive enough, the compression will trigger fusion again, this time with the helium in the core into heavier elements like carbon, with this process repeating for oxygen and neon. With every new fusion cycle, the star's internal pressure expands the diameter of the star until it begins the red supergiant phase of its life, when the core is being converted predominantly into iron. However, just like a Type 1a supernova, eventually balance collapses. This time it's because the star runs out of fuel. Red supergiants can't fuse anything beyond iron, so beyond this, fusion stops. And without this additional fusion energy pushing the star's mass outwards, electron degeneracy pressure on its own can't cope with the star's weight, giving a similar effect to what we saw with a Type 1a supernova. The only difference is that while some of a massive star will remain, often collapsing down into a neutron star or a black hole, white dwarfs usually vanish completely. Either way, the scale of material and energy released by a supernova is vast. So vast that unsurprisingly, anything immediately next to it is not going to last long. This is an energy powerful enough to rip apart a star. A planet is going to have no chance if it's in the immediate vicinity. Our own Sun, thankfully, will never go supernova as it's not massive enough, but if it did, there is a good chance the Earth would be either partially or completely vaporized, its rocky exterior reaching a boiling point thanks to temperatures 15 times hotter than the surface of our Sun, and being whisked away in the weeks of the supernova's passing. What is surprising, however, is how quickly this first wave of devastation would dissipate with distance. Indeed, vaporization is realistically not the largest threat a supernova poses. In 2011, experts from the University of Cambridge calculated that even planets orbiting their star at a distance of 15 billion kilometers, or about 100 times the distance between the Sun and the Earth, would remain intact and would instead simply be sent flying out into space now that there was nothing much left to orbit. Of course, such a planet's hypothetical ecosystem would probably have different problems to worry about. Things would get very cold very quickly. Of course, even if the crust of a planet itself remained intact, that doesn't mean that life on said planet would be sustainable. Ignoring the light of a supernova outperforming the brightness of an entire galaxy sometimes, leading to blindness for anyone who saw it, simply stripping away our atmosphere would carry problems. High levels of radiation, even if it didn't affect us directly, would alter the chemical composition of our atmosphere, negating our ozone layer, vastly increasing our odds of dying of radiation poisoning, and killing off phytoplankton in the ocean, and causing mass extinctions as the consequences of that worked its way up the food chain. scientists put this kill zone to be within 25 light years. Beyond that, the fury of a supernova begins to calm, as distance causes it to wear itself out. Although admittedly the asteroid that potentially killed the mammoths came from a supernova that was 250 light years away, if it happened at all, it was likely bad luck. Generally speaking, we wouldn't notice any damage from a supernova this far away. Its radiation levels wouldn't be high enough to cause mass extinctions. By 500 light years, we'd hardly notice the event at all, other than perhaps seeing a brighter star in the sky. So, feel free to breathe a sigh of relief. You are not in imminent threat from Betelgeuse. Although, incidentally, within 300 light years, are there any other supernova candidates we need to worry about? Thankfully, scientists are fairly confident that the answer is no. Massive stars are very noticeable, and the only two that are at risk of going supernova are Betelgeuse and Antares. Both of those are more than 400 light years away. White dwarfs are a little trickier thanks to their diminished brightness. They've been conventionally hard to spot, making it harder to predict whether we might be at risk from them. However, in 2013, ESA's Gaia Space Observatory released a massive packet of information in its efforts to map the stars that allowed scientists to identify 13,000 white dwarf stars within 326 light years of us. Thankfully, in spite of this large number, scientists remain confident that none of these are scheduled to explode anytime soon. Soon meaning within the next few 100,000 years. So we are safe from a supernova for now, and we can rest easy that when Betelgeuse explodes, it will likely not threaten the planet Earth. The shockwave traveling out from Betelgeuse would take some time to get to us, and even once it arrived, it would be traveling with less force than the push of the solar wind. It wouldn't be our magnetosphere or atmosphere that kept us safe. The protective sheath of the sun's heliosphere would be enough to keep such a supernova at bay. No harm will befall us on Earth, but it will make quite the spectacle, perhaps being as bright as a full moon, so even visible during the day. Just imagine that for a second. Seeing a supernova shining in our sky will still be a fascinating sight to witness, and on top of that, could reveal many secrets about the murky process of supernova explosions. So there's plenty of interest in Betelgeuse, much of it revolving around that singular question: when will it go off? Betelgeuse will detonate soon, although I say that in astronomical timescales. That means it could take anything up to 100,000 years. However, there are some scientists who predict that this red supergiant might detonate within the next few decades. Their research works under the assumption that Betelgeuse has a much larger radius than previously predicted, and if it's true, it might mean that we would get to see a local supernova within our lifetimes. But Betelgeuse does not give away its secrets lightly, and over the last few decades, it has thrown many curveballs at us. The inner workings of stars are complicated, and Betelgeuse dims and brightens according to several not fully understood cycles. It has a fundamental rhythm that's likely related to its eventual detonation, and several that are overtones, separate but connected. These cycles can range anywhere between a few hundred days to 2,170, and there is some debate about which of the cycles is its fundamental one and which are its overtones. As these are not fully understood, it always seems like something interesting is going on with Betelgeuse. It's been in the news a lot, like in 2009, when it contracted in size by 15%. You may have also heard, in 2019, that Betelgeuse underwent a great dimming, and scientists didn't initially know why. Speculations were running rampant that this could be a precursor to the promised supernova, although, perhaps sadly, this is likely not the case. New data from the Hubble Space Telescope suggested that the star itself may not really have been dimming, but rather that some dust which was ejected by the star may have cooled and obscured the view. In September 2019, Hubble saw heated material moving away from the star's atmosphere. Over the course of the next few months, this material was observed near the star. By December, the star began dimming in its southern hemisphere. It is theorized that heated carbon was in the outflow, and as it moved around the star, it expanded, which cooled it down. When we lost sight of it, it didn't move away from the star, but rather crossed over our view of Betelgeuse. At its peak, Betelgeuse was 2/3 dimmer than normal. However, since April 2020, Betelgeuse has actually returned to its normal brightness. So this cloud has either moved out of the way or totally dispersed. However, this event sparked renewed interest in Betelgeuse, and with that came an incredible discovery. Betelgeuse frequently brightens and dims in various cycles, but not all instances of this are likely caused by the star blowing off dust. At least one cycle might instead be the work of a tiny sibling. For over a century, scientists had wondered whether Betelgeuse might actually be part of a binary system, with a little companion star caught up in its gravitational pull. However, proving such a thing was a tremendous challenge, as Betelgeuse's surface was so unstable and fluctuating, being able to track the dimming and brightening that indicated such a star's passing was almost impossible. However, after the Great Dimming of 2019, far more researchers started turning their attention to Betelgeuse, and 2 independent teams found evidence that the longest cycle, the one running every 2,170 days, could only be explained by Betelgeuse having a neighbour. The key to proving the existence of Betelbuddy, as it's colloquially called, although its official name is Siwara, lay in looking back through radial and positioning data. Researchers at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, and another team from the Center for Computational Astrophysics at the Flatiron Institute in New York both looked at how Betelgeuse moved in the sky and noticed a tiny repeated variation over time, as if the star were being pulled to one side and then the other. This coincided with Betelgeuse dimming, suggesting a star was causing this effect. Both teams think that the smaller Betelbuddy is not much larger than the mass of the Sun and probably orbits a little less than the distance between our Sun and Saturn. Armed with this knowledge, other scientists jumped into the fray. First they tried with space telescopes, but were unsuccessful in finding a potential companion star. So researchers at the ground-based Gemini North Telescope in Hawaii turned the resolving power of its 8.1 diameter mirror in the direction of Betelgeuse to try to spot its furtive partner. Paired with a high-resolution camera called a speckle imager, which takes thousands of short exposure images to compensate for interference from Earth's obscuring flowing atmosphere, they were able to look at Betelgeuse when it was predicted this new star would be at its furthest point from the red supergiant. And sure enough, they found something. Although blurred, this is thought to be an image of Siwara, or Betelbuddy, so dim because its light is 6 magnitudes fainter than its volatile neighbour. This image is right at the limits of Gemini's resolution capabilities. While it's not a 100% confirmation, there are a number of other observations and predictions that this sighting appears to line up with, making it seem very likely to be the star researchers had been searching for. Though we'll have to wait until 2027 to double check, when it's next at its greatest separation from Betelgeuse. If this is true, it is a fascinating aspect of this star's continued story. It also helps us rule out the longer cycle as being the fundamental mode, the rhythm that dictates when exactly Betelgeuse is going to go supernova. Sadly for us, this makes it more likely that Betelgeuse will take longer to detonate, so perhaps it will not happen within our lifetime at all. Of course, while this is disappointing for us, it's probably a relief for Betelbuddy itself, which will be well within Betelgeuse's kill radius when it finally does explode. Predicting that moment, though, remains an inexact art, at least partially because much of what Betelgeuse seems to do is very confusing. For example, measurements from the ALMA array of telescopes have detected that Betelgeuse is rotating at a mind-bending rate of, well, just about once every 20 years. Okay, that might sound a little underwhelming, but for a star the size of Betelgeuse, this means that the surface is spinning at a speed of 18,000 kilometers per hour, or about 5 kilometers per second. That's 10 times faster than our own velocity on the surface of Earth, and for a massive supergiant star, it all but breaks the laws of physics. How do we know this? Let's start with the basics. There are a couple of different ways to measure the rotation of objects in the night sky. If the object is big enough, like the sun, the moon, or even a planet in our solar system, it's easy enough to point a telescope at it and watch its features move in real time. For reference, the angular diameter of the moon is about half a degree, and you can probably make out its features with your own eyes. Jupiter's angular diameter comes in at 1/100th of a degree, but its features are still clearly visible through a telescope. So, what about Betelgeuse? The supergiant star just 650 light-years away. For all its size, Betelgeuse is still far enough away from Earth that its angular diameter is 1,000 times smaller than Jupiter's, making it look like a total blur to even our most powerful telescopes. Luckily, there's another way to tell whether a star like Betelgeuse is rotating. It's less direct than just, well, looking at it, but it's an ingenious technique that relies on a simple effect you might have already heard of: Doppler shift. The same effect is also responsible for the change in pitch from a siren as an ambulance passes by. When the ambulance is moving towards you, the siren sounds higher pitched because the sound waves hit you at a higher frequency than if the ambulance were standing still. But as soon as the ambulance starts moving away from you, the effect reverses. Sound waves hit you at the lower frequency and the siren sounds lower pitched. What you probably wouldn't notice is that the Doppler shift affects light waves bouncing off the ambulance just like it affects the sound waves coming from its siren. The higher frequency light as the ambulance approaches makes it look ever so slightly bluer, and as soon as it starts moving away from you, the effect flips and it looks ever so slightly redder. The only reason this visual effect isn't obvious is because the speed of light is 1,000,000 times faster than the speed of sound, so it would take a much faster ambulance for us to actually notice the optical Doppler shift. We might not have ambulances here on Earth flying by at 5 kilometers per second, but those kind of speeds are fair game out in space, which brings us back to Betelgeuse. When a star is rotating, half of its surface will be moving towards us, while at the same time, the other half will be moving away. This creates a gradient of colors emitted by the star that we can observe with our telescopes, even if the star is too blurry for us to make out any of its distinct features. By seeing which side is bluer and which side is redder, we can infer the direction of rotation, and by measuring how different the bluer frequencies are from the redder ones, we can calculate the star's rotational velocity. This was the technique used by astronomers to analyze the data collected by ALMA and conclude that the surface of Betelgeuse was spinning at 5 kilometers per second. That's all well and good, except the known physics of spinning stars predicts that 5 kilometers per second is far too large a velocity for a red supergiant like Betelgeuse. Take our sun as an example. Its rotational speed is in the same ballpark, around 2 kilometers per second, but is also 1,000 times smaller and about 10 times lighter than Betelgeuse. If our sun expanded to the size of Betelgeuse, which would envelop the entire inner solar system and nearly reach Jupiter's orbit in the process, then its velocity would drop to just 2 meters per second in order to conserve angular momentum. In the same way that a spinning ice skater slows down when she spreads out her arms. And if the sun grew 10 times heavier to match the mass of Betelgeuse, its velocity would drop to 0.2 meters per second. So, the larger and heavier a star is, the slower we expect it to spin. And yet, Betelgeuse appears to defy all of those expectations. What's going on here? One possible explanation is that even though Betelgeuse didn't start out with this much angular momentum, it gained it through a process known as stellar cannibalism. As you might expect, stellar cannibalism is just what we call it when one star eats another star, usually its companion in a binary orbit. In more scientific terms, the star's gravity pulls away its companion's gas layer by layer until only the inner core remains. That gas carries most of the companion star's angular momentum, so the first star ends up not only growing larger, but also spinning faster than nature would normally allow. But is this really the story of how Betelgeuse got its spin? Or is there something even more mysterious happening under the surface? A team of researchers collaborating across Europe and China have recently suggested that Betelgeuse's apparently ludicrous rotation speed might just be a giant optical illusion. To see how that's possible, let's think back to what the team at ALMA really measured with their state-of-the-art array of telescopes. Though their pictures of Betelgeuse were blurry, they were still able to make out that one half of the star emits slightly redder frequencies of light than normal, while the other half emits slightly bluer frequencies. The obvious explanation for this 50-50 split is that the star is rotating, with one half moving towards us and the other half moving away from us at the same time. The green arrow in the image of Betelgeuse is meant to represent the axis of this rotation. But what if that's not the only explanation for the color gradient detected by ALMA? Simulations of Betelgeuse have revealed that its surface is a chaotic, turbulent place, constantly bubbling under its own heat like water bubbling in an oven. Each of these bubbles is enormous and propagates outwards at deadly velocities. A single bubble can be 100 million kilometers across, covering a large fraction of the surface of Betelgeuse. And if one of these bubbles were headed your way, even today's most powerful spacecraft wouldn't save you from its lightning fast speed of up to 30 kilometers per second. Your only hope would be for the bubble to pop and crash violently back down onto the surface before it ever reaches you. As gas bubbles all over Betelgeuse rise and fall, its surface becomes a mosaic of regions that are either moving towards us or away from us as observers on Earth. In turn, the Doppler shift causes light emitted from these regions to be either blue shifted or red shifted. In a recent paper that rose to challenge all previous explanations of Betelgeuse's rotation, the international team of researchers proposed that Betelgeuse might not be rotating fast at all. Instead, the ALMA observations might be detecting a range of light frequencies coming from Betelgeuse due to the turbulence on its surface. Thus, astronomers may have been misinterpreting those shifts in frequency as rotational effect. But if you've been paying close attention to the physics, you might have noticed that there's still a loose end with this alternative explanation. A rotating star should produce a smooth gradient of light frequencies, ranging from bluer than expected light on one edge to redder than expected light on the other. Meanwhile, a turbulent star should produce a random patchwork of colors, with bluer patches where bubbles happen to be rising and redder patches where bubbles happen to be falling back down. How could the astronomers at ALMA possibly have mistaken one for the other? If astronomers observed a smooth gradient of colors coming from Betelgeuse, shouldn't the patchwork explanation already be ruled out? In an ideal world, that would be true. Gradients would correspond to rotation, and patches would correspond to bubbles. But remember that Betelgeuse is so far away that the image captured by ALMA is far from ideal, and it's more of a blur than an HD photograph. When simulations of the surface of Betelgeuse are made to account for the limited resolution of observations, they predict that the bubbly patches of redshift and blueshift will be easily mistaken for a rotational gradient about 90% of the time. This means that even if the astronomers at ALMA did nothing wrong in their analysis, they may have been fooled by Betelgeuse's boiling surface into thinking it's spinning way faster than it actually is. This also means that astronomers are now chasing after one key objective: higher resolution studies of Betelgeuse that could more accurately tell the two scenarios apart. The good news is that better images of Betelgeuse already exist, taken by the same telescope but with longer exposure times. The bad news, for those of us who are more impatient, is that it will likely take a couple of years for them to be properly analysed. Those answers are coming though. For now, I'm curious to know where you would place your bets. Is Betelgeuse really spinning at 5 kilometers per second after having eaten its companion star? Or will the new claim that this rotation speed is nothing more than an optical illusion be vindicated? So there you have it, everything you might want to know about Betelgeuse, a star on the brink of cataclysm. It is no wonder we hold such a savage event with such fascination. Humans love explosions, as every culture's love of seasonal fireworks attests. So whenever it comes, a supernova detonation that lights up the night sky will be awesome to behold. Though I'm glad that in Betelgeuse's case, it will be from a very safe distance. Special thanks to MyHeritage for sponsoring this video. If you want to find out about who you are, scan my QR code or click the link in the description below to give MyHeritage a try with a 14-day free trial. Thanks for watching, and a quick shout out to Brian Lyles. Thank you for being a Supernova tier astronaut and supporting us on Patreon. If you want ad-free videos, wallpapers, and to join a community of hundreds that love space, sign up below so we can finally reach 1,000. It's more than a number, it's a milestone for everyone who's been part of Astrum's journey. Each new astronaut makes this constellation bigger, the conversation deeper, and the experience richer for everyone. Now's the perfect time to join the community.